I'm going to show you how to do 17.1, but actually you don't need to turn in 17.1. What you need to turn in is 17.2, but 17.2 is very similar to 17.1. So you just follow what I'm going to do in 17.1, then you just write up 17.2 and submit 17.2. So let's take a look at question 17.1 first. So GMAT. So this is a time that where you should pause the video and read the question yourself. Okay, so I assume that you have done that. The first question you always ask yourself is, what am I measuring? Are we measuring height, weight, or what? So clearly we are measuring GMAT scores. And so a researcher in Philippines, what does that researcher in Philippines want to achieve? She believes that, so here's a key sentence. She believes that the mean score, so I don't understand why there's an S here. It should be just one mean score. For this year's college senior in the Philippines, the mean score probably should be less than 550. Now, so she's challenging the assumption of 550. So 550 here is the assumption. But she thinks it should be less than 550 in the Philippines. So what does she do? She'll go and collect a sample of 250 students and figure out the sample mean. So what are the questions asking? So there are three subparts. A, we seek evidence against. So what the researcher is doing is to find the evidence against the claim, the assumption that mu is 550. And then it asks you to draw a density curve and so on and so forth. And then B and C gives you each subpart gives you a different sample mean and asks you to compare which one gives you more evidence. So we're going to do A first. So now, as I said, the most important thing is you understand what the question is asking. What are we measuring? And you know the assumption. So please write what the individual elements represent. The individual element here is a GMAT score for a test taker in the Philippines, and the mu is the population mean GMAT score in the Philippines. You are told that X is normally distributed. That means the population distribution is normally distributed with this mean and this standard deviation. So what does it tell us? Here, the mean score, this sentence, the mean score of all test takers is 550. All test takers, right? So 550 is the mean of the entire population with a standard deviation of 120. So this researcher is using this number as her assumption, okay? So mu is 550, so X is 550 with the center, sigma 120. She takes one sample size, 250. The researcher thinks that mu should be less than 550. So please write out all these information in your question. The reason is that later on in chapter 17.3 and 4, you have to make, after you do calculation, which is a simple, easier part, you have to make conclusion. And making a conclusion is the most tricky. So the clearer you set up all this information up front, the easier it is later on for you to make conclusion. So we're going to do A, B, C, but let's do A first. Question A, subpart A asks you the sampling distribution of the sample mean. So X is normally distributed. So X bar is also normally distributed. And the center of all sample mean is mu. The standard deviation of all sample mean is sigma divided by square root of n. Okay, so sigma divided by square root of n. So this number actually is 7.589. So let's round off to 7.59 for a calculation. So what are we supposed to do next? We are supposed to draw the density curve of this distribution and mark on the axis the values of the mean and 1, 2, and 3 standard deviations of sampling distribution on either side of the mean. So here it is. So I'm going to so this is our density curve, like the smooth version of the histogram of all possible sample means of the size 250. So the middle part is 550. I'm sorry, of the size 250. Okay. Now, so we have to do markings, plus 1 standard deviation, plus 2 standard deviations, plus 3 standard deviations, so on and so forth. So let's just calculate that. So mu plus 1 standard deviation is 550 plus 7.59. This is 557.59. And then you have to calculate mu plus 2 standard deviations is 550 plus 2 times 7.59. Okay, and then you have to do mu plus 3 standard deviations, so on and so forth. And you also need to do mu minus 1 standard deviation, mu minus 2 standard deviations, and mu minus 3 standard deviations. Okay, so you figure out all these 6 numbers, and then you can do your marking here. So let me quickly do this. So this is vanilla space. Let me erase this. On the other hand, on the other side, mu minus 1 standard deviation, y42.41. Should be a 4 here. Double check. Okay, good. So I have 6 markings, plus 1 standard deviation, plus 2 standard deviations, plus 3 standard deviations, minus 1 standard deviation, minus 2 standard deviation, minus 3 standard deviations. So what's next? B and C are very similar. So B gives you a sample mean, mark this point on the axis. C, another sample mean, and then it asks you why one sample mean is good evidence against the assumption, and why the other sample mean is not good evidence against the assumption. So we have 2 sample means here. So again, so in real life, we typically only conduct one sample. We only select one sample because selecting one sample is already pretty expensive. But for learning, for illustration purpose, we assume that we have 2 sample means. So one is 542, the other is 532. So 542, where does it go? So this is 542.41. So 542 is somewhere here. So this sample mean is located roughly, this is the mu, roughly 1 standard deviation below the mu. 1 standard deviation below the mu. Another sample mean is 532. 534 is here, so 532 is somewhere here. So this one is 532. So where is this 532 in relation to the mu? So it's roughly 2 standard deviations, a little bit more than 2, but roughly 2 standard deviations below the mu. Okay, so from this diagram, you can easily tell that this sample mean, 532, is farther out from the mu, and therefore 532 gives you stronger evidence against the assumption.